of our textbook, let's talk about moving beyond nonlinearity. In today's lecture, we are going to explore many different ways of controlling nonlinearity. Why? Because the truth is almost never linear. So no matter what, unless you have just simulated your data based on the linear model, your model is barely linear. So what we need to do is either refer to our linear models, because although they're not linear almost all the time, they often make a very good assumption. That's a very good assumption most of the times, and it's very interpretable. However, there are some instances that the linear model is not useful because the assumptions there is very strong. So we need to move beyond that, and there are so many ways to go beyond it. We can use polynomials, one of the thing you got we discussed before. We can use the step functions, and then more advanced versions of the step functions. We move to splines, and then we can work on local regression models and generalized additive models. Today we have a lot of techniques to cover. Some of our techniques, including polynomials, are something we discussed before, but most of the thing might be quite new to you. So let's see what we have today. So let's work on polynomials. Polynomial is the basic, or perhaps the first thing comes to mind to control for nonlinearity. One of the great things about polynomials is that what you need to do is just introduce some other functional forms on your input variables, like cubic, square, degree 3, or up to degree d, and then you can just put it in a simple linear regression line. So for example, you just assume xi2 is a new variable which has all the values of x to the power of 2, and you just define xi3 as a new variable which has all the values of x's cubed, and so on and so forth. So basically, estimating these parameters is equivalent to estimate a simple linear regression model parameter. So beta 0 hats to beta d hats can easily be estimated. One of the problems of using polynomials is that although it's extremely easy to estimate it, whenever your degrees of freedom or degree of polynomial is more than 4, or even for 4, the confidence intervals you get at the tails become wider and wider and wider. Specifically, if you go after degree of 4, for example, degree of 5, these confidence intervals become so bad behaved. So in order to control for that, we have to use more advanced models. So here, what we see on the left-hand side panel is age versus wage. So we have so many observations of different people in different age groups, and we have their wage. And so we want to see what is the relationship of wage and age with polynomial degree 3. For example, we have some high earners here. Those are the people who earn more than 250K. We have medium class here, and we have other classes around it. So one thing we can see that with this 4-degree polynomial, what we can see here is that from 40 years old to maybe 55 years old, that's the peak of our earning on average. Before that, our earnings grow, and after that, when we retire, let's say around 65 or 70, our earnings drastically, on average, shrink. And that is quite natural. So this nonlinear shape captured this nonlinearity here, but as you can see, our predictions are at the tails of our distributions, or at the tails of our data are not that reliable. On the right-hand side panel, we have probability of wage being more than 250. So we introduced an indicator variable, whereas if there are some observations that are 250K and above, that is 1. If if you're low income earner and your income is less than 250, you're set here. So you want to see how the probability of becoming a high earner will change by age. So we use just logistic regression, but in the function we use nonlinear terms. So exactly the same thing we did here, with the only exception that we've just put that function in exponential and divided by 1 plus exponential of that function. So we get this nonlinear. Again, we see that the probability of us becoming, on average, a high earner is very slim when we are below 30. Then when we are around 35 and up to 60, that probability increases. Although it's still slim, it's around less than 5%. It increases by age, but after 65 it starts decreasing. But look at this confidence interval around these tails. Again, what we can see is that our nonlinear model of polynomial degree 4 didn't do a great job for this prediction. One thing to notice is this. Here you see 0.2 probability. That means if you just scale everything up to 1, this confidence interval doesn't look as bad as it looks now. But again, it's not tolerable. The confidence interval is so large. Your prediction for a person who is 80 years old is from 0% probability to become a high earner up to 20%. It's ridiculous. It doesn't have that much predictability for this tail. So to sum up, in order to use nonlinear regression models, or better say, linear regression models with nonlinear terms, what we do, we just introduce some functional forms on input variables, and we just run a simple linear regression line to define these models. So this x0 can be considered as x1, x0 squared can be introduced as x2, and so on and so forth. So basically, estimating beta hats is equivalent to estimating beta hats in a simple linear regression model. And once we estimate these parameters, it's extremely easy to find the variance of them by point by variance method. We introduce an expression for pointwise variance of these functions at any point, and then once we have that, the estimate of our models will simply be the estimate of your prediction plus minus the standard error you get from this variance pointwise. So the point is, it's extremely easy to implement polynomials, polynomial regressions. We can estimate the errors both for simple linear regression models and also in logistic models. So in logistic models, everything is just the same as simple linear regression models, except the fact that in exponential terms, we have degree 1, degree 2, up to degree d polynomial. Again, estimating beta 0, beta 1, and beta 2 to beta d is equivalent to estimating the simple logistic regression model parameters, because we can just redefine xi as x1, xi2 as x2, so everything will come equivalent to whatever we had before on logistic scale. It's a pretty standard way to do that, but again, what we observed here was that when you run such regression models, the estimates of your error at the tails are not tolerable, specifically when d is more than 4. So what can we do in order to solve this problem of very bad confidence intervals at the tails? There are so many techniques. The easiest way to do that, and perhaps not the most genius one and not the most applied one, is called step functions. In the step functions model, what we do is simple. We just divide our data into different groups, and within each group we just estimate what is the outcome for that group. So the idea here is very much the same of decision trees, if you believe it or not. In decision trees, we would divide our data set into different groups, and for each point or each region, we would assign one prediction for that. So in the step functions, we do exactly the same thing in a slightly different way. And what we do, we just divide our data set into different groups that we believe these groups are really different. For example, in this data set, wage versus age, what we do is that we separate our data, we split our data to people who are less than 35, people who are between 35 and 50, people who are between 50 and 65, and people who are more than 65. So this is C4. So C3 will be I of X being between 50 and 65. So you may ask me, okay, why did you divide your data set into 4 groups? That's a very valid question. You could divide it into any number of groups you're comfortable with, but you should have some natural assumption behind it. Perhaps it might be better that you would consider it as 18 to 24, which is this student lifestyle, and then 24 to 30, which is the beginning of the career lifestyle, and so on and so forth. But let's focus on the current split of data. We have 4 groups: people who are less than 35, people who are between 35 and 50, people who are between 50 and 65, and people who are over 65. So if I want to show it here, we have people who are 35, people who are 50, people who are 65, between 50 and 65, and people who are 65 and above. So a prediction for people who are between 0 and 35, better say 18 years old to 35, is that line. So on average, we expect to earn something around 90K with this confidence interval. For people who are from 35 to 50, this is our prediction, that is 120. And people who are from 50 to 65, almost the same, so our eyes cannot show the difference of this step. And later on, for people who are more than 65, this is our prediction, and this is our confidence interval on average. So on average, we predict they earn this much. In order to find these step function, what we need to do is just define these dummy variables or indicator variables, and we just run it in a simple regression line. The coefficient we find would plus the intercept would just show these amounts. We can do the same thing in logistic regression lines, and we just divide our data set into the same groups, and we just put these indicator variables inside our logistic regression line, and that will be our predictions for these age groups. So for example, our prediction for people who are less than 35 is that you only have very slim chance, let's say 1%, to be among top earners. When you become older, this probability increases to, let's say, 0.4, then later on from 50 to 60, the probability increases just a little bit more, and lastly, after 65, the probability decreases to 2% again. So this is the simple step function method. These guys, these partitions are called knots. So this decision or not on knots are somehow arbitrary. They should reflect something natural, but they do pretty good. They're pretty easy to interpret, and that's why the most application of them are just some reports that normal people read. For example, in newspapers or other means of news, for example, CNN or other types of news broadcasts, that the people who watch it or don't have any statistical background. So that's so easy to interpret that you can use it there. But for us who want to get involved in more sophisticated models, that is not the best thing we can do. So they're easy to work with. You just use series of dummy variables. The great thing is we can make it more sophisticated by adding the interaction term. For example, if you were interested to add interaction term age with year, you could do that, and that would result in functions like this on here. They're not necessarily continuous, but since we have added age as an interaction term here, then you let it have some nonlinear, have some slope here. So we get rid of these constant functions. And the way you do it in R, but to introduce these knots, is by using a function called cut. So we are going to explain it in our R session, so don't worry. But basically, what you need to do is you just define the variable you want to split, and these are your cuts. So say, okay, I start from 18, then I have my first cut at 25, then the 40, then 65, 90. So you automatically divide your space into 4 different cuts. So what we observed here was these step functions are great. We can use any type of interaction here to make it have a slope, but there is no guarantee of continuity, and that's a problem. For example, let's say this is our predictions for age. So right before your age, this is your prediction. Right after your age, this is your prediction, and that's the problem. How can your prediction for somebody who is 34.9 years old is, let's say, 80K, and people who is 35.1 years old, 120K? It doesn't make that much of a sense. So we're trying to solve this problem. We are using something more useful called splines. But in order to get there, I have to introduce I have to discuss how you can add nonlinearity there as well, because another thing that we are lacking here is nonlinearity. So in general, we can introduce piecewise polynomials instead of step functions. And that the way it works is that, okay, you would say, okay, I want to split my data on a knot called C. Before C, I want to have degree 3 polynomial, and after that, I want to have another degree 3 polynomial, something like this. And the way you do it is, okay, before C I have one polynomial. After C, this knot, I have another polynomial, and that's the idea behind the splines. But not only this condition should hold in the splines, but also they should be continuous. So let's see what the splines do. So here we have a bunch of examples of piecewise cubic functions. For example, here we have a non-continuous piecewise cubic function. As you can see, it took care of nonlinearity before 50 years old and after 50 years old, but right before 50 years old, your assumption is so different from right after it. It's almost 20K difference. We can solve this nonlinearity by we can solve this continuity by imposing a continuous limitation on it, so make sure it's always continuous. So let's look at this function. This function looks better than this one, but as you can see, at that 50 we see this kink. So it's not a smooth function. Here we again look at a cubic spline, the first spline we are going to discuss, the most famous splines, by the way. It's not only continuous, but it looks smooth. As we will learn later, whenever your eyes cannot tell the difference of these two different functions before and after a knot, that means these two functions are not only continuous, but also are continuous on their first degree derivative and their second order derivative. And here we see a linear spline. There's no way to make this linear spline without a kink, because the first order derivative of these functions are constant. So if we wanted to have just a smooth line, that should be just the continuation of the first line, but what was the point of that? So let's look at linear splines. A linear spline will have, with k knots, have k knots at psi k's. For example, in the example of age versus weight, we had three knots. One knot was at 35 years old, one was at 50, the other one was 65. So psi 1 was 35, psi 2 was 50 years old, and psi 3 was simply 65. So whenever you want to use a spline, so we should decide on knots. So our knots are psi k, we can have 1 to k knots. So in the example of way, we had 3 knots. Then you write your spline this way. You have some base functions, which are the base functions of beta 1. These are base functions. And some coefficients. And these are betas. So base functions are fixed. These coefficients are going to be estimated. So based on number of coefficients, betas, that needed to be estimated, your spline will have that many degrees of freedom, or that much flexibility. So the basis functions look like this. On a simple linear spline, when you only work with lines, so this is the simple linear spline, your base function is only a simple one-to-one relationship from xi to xi. So that is b1. Your bk plus ones are knots. These are the not related base functions. Looks like this: psi xi minus psi k, and remember these psi k's were not at k, plus. That means they are 0 before psi k, and they become xi minus psi k right after it. For example, xi minus 5 plus. So let me call it beta, let's say this is our first knot. So what is beta 2 of 3? Beta 2 of 3 is, see, 3 is less than 5, the knot. So 3 is less than 5. So beta 2, 3 is 0. How about beta B2? Sorry, I kept saying beta. It's B2. B2, let's say 10. B2 10, since 10 is more than 5, this is 10 minus 5, which is 5. How about B2 5? B2 5 is, you can just put it in any part of it. So okay, 5 is greater or equal to 5, or it's just less than 5. But irrespective of what you choose, it's 0. So that's why these base functions are continuous. So what we learn here is that these based functions, before those knots are 0, and right after those knots are the difference of what you observe and that knot. So in essence, they look like something like this. So there's 0 before it, and then they go at 45 degrees up. And here it's their knot. So that is the simple linear spline knot. So for every knot, we will add that, and let's see how it will look like. So here we have a function. We have a linear function before it. So remember, this is the functional form we have. So here we had y was equal to, let me see, it's 0.3 plus 1 times x. Yes, I think that is 1 times, no, it should be smaller. It's 2, is half times x. Yeah, 0.5 times x. Yeah, that is 0.5. Okay, so let me erase it. Oh, I never used that eraser before, but it looks cool. Okay, so 0.5x plus, so R naught is at 0.6. So we had x minus 0.6 plus. And let me see what is this, what is the slope of that. So that is 0.6, that is okay. So let me see how much effect it had. So at 1, it became 0.8. So at x1, it should become 0.8. So that is 0.4, that is 0.5. So that would be, okay, so it's negative 1. It seems like this is negative 1 times x minus, no, it's not negative 1. I'm sorry, that's my mistake. It's a negative number for sure. So let's see. So at 1, it should become 0.8. So this will become 0.4 here. This is 0.5, this is 0.8. So I said at 1, it should become 0.85, let's say. At 1, at x equal to 1, it becomes 0.85, for example. Okay, so if that want to happen, then it's negative 0.25, let's say. Negative 0.25, or like even a smaller, negative 1. Okay, it's negative 0.0125. 0.125. So it's negative 0.120, negative 0.125 times x minus 0.6 plus. So let's see what this function does. So first of all, this is beta 0. This is beta hat 1. And this negative number is beta hat 2. This is our first knot, so that's b2. This x is our first base function, that is b1. So b1 and b2 has not been estimated. These were given to us. These three numbers, beta hat 1, beta hat 0, and beta hat 2, were the estimates we found. And the more knots you add from here on, the more coefficients you need to estimate. But as you can see in linear models, what we can prove is this continuity. Why? Because right before 0.6, this function becomes 0. Right after it is also 0. So that's why it's continuous. But after that, the slope has changed. We can go further and just use a more general form of splines, and this is the cubic spline. That is one of the most famous splines out there. It's not as useful as some of the other splines that we're going to discuss, but in the general term, the most easiest way of showing it, it's simple to use, and that is called the cubic splines. The cubic splines have three base functions all the time. So irrespective of how many knots you have, beta 1 is xi, beta 2 is xi2, and beta 3 is xi3. From there on, anytime you have a knot, you just add xi minus that knot cubed. For example, only the positive part of it. So for example, let's define B4 as xi. So let me call it bxi. Sorry for very bad handwriting. So bxi, let's call it xi minus 3 plus cubed. So that means b4 of 2, or any other point which is less than 3, this is 0. b4 5 would be 5 minus 3 cubed. So 5 minus 3 is 2, and 2 to the power of 3 is 8. So these are our base functions in the cubic format. Something great about this, showing it in this way, is that if your function will be continuous at psi k, any naught. Also, the first order derivative of that will be continuous, and also the second order derivative. So that's why when you use cubic splines, right on your knot, you do not see any, you see everything on knot is very smooth. So let's prove that these types of splines are continuous at the first, second derivative, and also they're continuous as well. I assume we only have one knot. I just define my knot as psi k. So here is our function y. So y will become beta 0 plus beta 1x plus beta 2x2, because these three base functions, x, x2, and x3 should always be there. So we only have one beta 4, because I said we only have one knot. You can extend it to any number of knots, by the way. So let's see what will happen. So let's look at y right at psi 1. So slightly before psi 1, this function is 0, right? Because x is less than 0. So slightly before psi 1, you can write it psi 1 negative. That means slightly before it. That's a notation you can use. That is beta 0 plus beta 1 psi 1 plus beta 2 psi 1 2 plus beta 3 psi 1 3 plus 0, right? Right after that, so you can write, or right on that point, you get the same thing. I'm lazy, I just put same thing plus beta 4 times psi 1 minus psi 1 cubed, which is 0. So as you can see, right before psi 1 here, right after psi 1, you get the same result at y. So it's continuous. So continuity is just being proved. So now let's look at first order derivative. So when x is less than psi 1, so this function is 0, so our first order derivative, with respect to x is beta 1 plus 2 beta 2x plus 3 beta 3 x2. And since this part was 0, nothing would change. So this function at psi 1 is beta 1 plus 2 beta 2 psi 1 plus 3 beta 3 psi 2 psi 1 2. Sorry for my very bad handwriting. My notepad cannot do better. So when x is more than psi 1, this function becomes in place. So first order derivative with respect to x will become same thing we had before, 2 beta 2x plus 3 beta 3x2 plus 3 times beta 4 x minus psi 1 squared. So let's see what that number will become at psi 1. That will be beta 1 plus 2 beta 2 psi 1 plus 3 beta 3 psi 1 squared. But look what will happen here. Psi 1 minus psi 1 is 0, so the last part is 0. So this function is continuous, and this first derivative as well. I leave it to you to prove it's also continues on its second derivative, everything will be easy. You just need to take another derivative of this derivative and look what will be at psi 1 and take another derivative of this derivative. The last part will be 6 beta 4x minus psi 1. And you can show that this is also 0. This part is also 0. So these two functions will become the same. Therefore, they're continuous at their second order derivative as well. So that's the power of splines. So you just show that on each node or not, they're continuous on their first derivative, and they're also continuous on their third derivative. That's what is wonderful. Sorry, not third derivative, second order derivative. So here you would see that if this not didn't existed, my original base function, which was y was equal to beta 0 plus beta 1 x plus beta 2 x2 plus beta 3 x3 would become this blue line. But since we had beta 4 times x minus epsilon 1 plus 3, by the way, epsilon 1 here is 0.6. This shape has changed based on the original shape we had. So this is simply x minus psi 1 cubed, or x minus 0.6 cubed, okay? When you multiply it with the function you had, with the parameter you had, which was a -1, it would change the shape of everything. So when you add this negative function to original one, you get this as the changed shape. So what we see here is that in this not only it is continuous, but also it's continuous with first derivative and third derivative. Why do I say third derivative? Second derivative, I'm sorry. So it's easy to show that in cubic splines. If you have k parameters, if you have k knots, since you always have these 4 parameters to be estimated, beta 0, beta 1, beta 2, and beta 3, and you will have k basis function in terms of knots, the degrees of freedom, or in other words, number of parameters needed to be estimated, would be k plus 4. So in cubic splines, you need to estimate k plus 4 parameters, beta 0, beta 1, beta 2, beta 3, up to beta k plus 3. There is another version of the splines which do slightly better than cubic splines at the end, at the tails, which are called natural splines. In natural splines, you put 4 more constraints, and what you do is that you make sure at the tails you have linear functions. So you have cubic splines in the middle, and you have at the tails you have linear functions. Why do we do that? It's because let's focus on just cubic splines. This blue curve, which almost looks the same on every point, but the tails on this data will again create very ugly confidence intervals at these tails. Why? Because they are cubic functions. You don't like it. You don't like cubic functions. They're of course better than polynomial degree 4 or degree 5 function, but still not the best thing we have there. So by forcing the tails to become linear, what we do is that we will make sure we will have a smaller or narrower confidence intervals at the end. So this red curve represents a natural cubic spline. That's the name of these splines. And as you can see, they behave so much better at this tail because the the confidence intervals are narrower than cubic spline. So if you have a choice between natural splines and cubic splines, I would suggest you use natural splines. And natural splines have degrees of freedom equal to k. And k is number of knots you have. So the function you use in R for basic splines is BS. I don't like the name. I don't know who came up with this name. And natural splines is NS. We are going to cover that extensively in our sessions. So now let's see what we achieved by using natural cubic splines. So in this red curve represents a natural cubic spline with degrees of freedom 14. That means it had that many knots. At the same time, we showed that what would happen if we would use polynomial with same degrees of freedom, and that would be polynomial degree 14. So as you can see, in the middle where polynomials do a good job, splines and polynomials are almost the same. But at the ends where polynomials do a terrible job, these natural splines just took care of that terrible decisions that they make. So as you can see, it's almost preferable to use natural splines than polynomials of degree 3 because of that very bad behavior at the tails. And another thing that I want to emphasize again is that if you have k knots in cubic splines, you use k plus 4 degrees of freedom. In natural splines, we only use k degrees of freedom. So if you have, in the previous example where we had wage, if you had 3 knots, then you would have 3 degrees of freedom for natural splines, but 7 for cubic splines. So in what will follow, I'm going to introduce another type of splines to you, and these are called smoothing splines. I covered it in my next video. So I see you in my next video.